Good evening. As Councilwoman Henley stated, I'm the emergency manager for the City of Virginia Beach. For those of you that aren't quite aware of what I do, I help prepare, respond, and recover from disasters here in the City of Virginia Beach. Work very closely with my counterparts throughout the region as we're all dealing with this issue. I was asked tonight to come and help moderate this event. Both Mr. Sammler and Mr. McCoy with the National Weather Service and the National Geological Society. I have a great deal of contact with them and work very closely with them, and they have a great deal of insight to provide for this evening. They're both going to speak. We're going to allow for questions after each speaker, so you don't have to save it up. We will also allow time at the end because we want to continue moving forward. So after the first speaker, we'll have about 10 minutes or so of questions, and we'll have the second speaker, another few minutes of questions, and then some extended time if we do, because I believe we're headed to close out at 8 o'clock, but both will be available afterwards as well. So to kick things off, Mr. Sammler, Bill Sammler, is from the National Weather Service out at Wakefield. He is the External Emergency Management Liaison at the Wakefield office. The Wakefield staff supports Central and Eastern Virginia, Northeast North Carolina, and the Lower Maryland Eastern Shore. He coordinates the state and local emergency managers, he's very important to us, state agencies, the media, and other National Weather Service customers to ensure that National Weather Service products and services meet their needs. Bill participates in various training initiatives and assists with a variety of weather-related exercises. Bill came to Wakefield in April 1994 after spending his first 10 years of his nearly 35-year National Weather Service career at the National Severe Storms Forecast Center in Kansas City, Missouri, now the Storm Prediction Center in Norman, Oklahoma, issuing nationwide forecasts for severe thunderstorms and tornadoes. He has received several awards, including the 2005 National Hurricane Conference Outstanding Achievement Award in Meteorology. He's a native of southern New Jersey. Bill and his family live near Petersburg, Virginia. He has a Bachelor's of Science degree in meteorology from Rutgers University and a Master's of Science in Meteorology from St. Louis University. If you would please welcome Mr. Bill Sammler for this evening.
Thank you, Erin. Good evening, everyone. If it's okay with you, I'm going to move around a little bit because I feel like I'm in jail behind one of those podiums. So if we could start my presentation, and I'm going to focus my presentation on hurricane dynamics, specifically as they relate to some of the things that you all as citizens of Virginia Beach have A, experienced, or B, could experience. So one of them that I will show fairly early on in my presentation is one that probably most, if not all of you, are familiar with here. So we're going to start talking about rainfall. And it is, as Councilwoman Henley said, really timely because we had an event that was not too dissimilar, although nowhere near as dramatic as an event we had a couple of years ago. But there's some things you need to know about Matthew that are critical in terms of your understanding of why Matthew was Matthew. So let's start with something that's really important, and that is an understanding of where rainfall typically occurs for most of the tropical storms and hurricanes that we experience here in Virginia Beach. For the most part, once a storm makes landfall, and you can go back and look, and I've got two up here. I've got Irene on the left and Floyd on the right, both significant rainfall producers in Virginia. But you can look at other events, including Matthew, which I'll show in a minute. And in the vast majority of situations, the rainfall, at least the heaviest rainfall, ends up on the left-hand side of the track. That's primarily due to the fact that dry air ends up getting entrained on the ocean side of the storm, and it throws all of the precipitation to the left side. There are other things that go on, but that's a strong part of it. Not every hurricane or tropical storm does that. And if any of you were here 15 years ago and experienced Isabel, you know that Isabel was not a big rainfall producer. In fact, lots of Southside Hampton roads got an inch or less of rainfall from Hurricane Isabel. But if you look at the pattern with Isabel, you'll notice that the rainfall is pretty uniform on both sides of the track. That has a lot to do with the track itself, plus other factors that weren't part of Isabel's dynamic that are typically part of the storms that we normally see that affect Virginia Beach. So if you keep those two slides in mind, we can sort of get a sense of what happened with Matthew. So the first bullet may be the most important bullet for you to remember relative to why Matthew was Matthew in terms of its impact on Virginia Beach. It wasn't the only heavy rainfall event that occurred. It was the third big rainfall event that affected not only Virginia Beach, but Southside Hampton roads and adjacent Northeast North Carolina in a span of about 6 weeks. All three of them were due to tropical systems. Matthew also interacted with a cold front that was dropping to the south. That enhanced the winds and made Matthew not a truly tropical system as it impacted us. And I'll show you a little more about the wind later. There were some problems with storm surge and erosion, but not as bad as it could have been. And I'll show you a little bit of evidence of that in a bit. The other important thing, and you all probably remember this if you remember anything about Matthew, is that the track forecasts 3, 4, 5 days out were nowhere near, and actually even 2 days out, weren't anywhere near as helpful in understanding what the potential impacts of Matthew were going to be as they normally are. If you remember, Matthew was forecast to make this big horseshoe loop and turn south, but it never did that. And that's a little bit unusual to be that soon into an event or that close to an event, and for it not to, for us not to do better when it comes to the track forecast. So here's the track of Matthew. Basically stayed offshore, except for a little bit of time when it made landfall in South Carolina, but it's basically an offshore system. But if we look at the rainfall relative to the track of Matthew, you can see that Matthew sort of played according to Hoyle, and that virtually all of the heavy rain with Matthew occurred left of the track. And that's typical of most tropical systems, hurricanes or tropical storms, that affect us here in Virginia Beach. If Matthew in and of itself were just Matthew, under quote-unquote normal circumstances, the impact would have been very different. But the reality is, it wasn't the only event. So in the grand scheme of things, and you can go back to Floyd and you can go back to other events that we've experienced here where we've had significant flooding, and that is rarely is a single heavy rainfall event the reason for a broad, significant impact in terms of rainfall-related flooding. It's almost always multiple events. How wet the soil is, how high the rivers are, makes a difference when it comes to, in the case of Matthew, a climatic event in terms of it being the thing, the event that sort of what broke was the straw that broke the camel's back, so to speak. What happened in September with the other two rainfall events allowed the impact of Matthew to be as bad as it was. So, and the other thing is the rainfall pattern, and I'll explain this in a little bit because it has to do with where water goes, resulted in many cases in the impacts that you all experienced. So here's the September rainfall. Huge area in eastern North Carolina, southeast Virginia got 10 or more inches of rain. Some places got more than 15, one or two places actually were up close to 20. Now to give you a sense of what that is, that's anywhere between 3 and 5 times the normal rainfall that we would expect in September. So it was a big deal. And the antecedent or pre-storm conditions prior to Matthew were wet. And in some cases, really wet. What you don't want before another big rainfall event. Here's where the heaviest rain with Matthew occurred. And the circle that I have there is in exactly the same place as the circle in the previous slide. So the heavy rainfall from Matthew occurred almost exactly the same place that the heavy rainfall in September occurred throughout the south side part of Hampton Roads. The other thing to notice is the rainfall with Matthew extended south and southwestward into northeast North Carolina. That's important because the water in at least the southern half of Virginia Beach, Chesapeake, Suffolk, Southampton County, goes the same place that the water in eastern North Carolina goes. So it wasn't just the rain in Hampton Roads that was a problem, it was the rain in Hampton Roads plus the rain in eastern North Carolina that helped create the situation and the impacts that you all experienced. So where does water go? Well, if you want to use a roadway kind of as a gauge, you go north of 264, the water goes into the Chesapeake Bay. You go south of 264, and that's kind of a rough estimate, the water goes into the Albemarle, Currituck, and Pamlico Sounds. So you might say, well, why is that important? Well, the Chesapeake Bay has about a 14 or 15 mile wide mouth that allows an awful lot of water to go out of it. The Albemarle and Pamlico Sounds have 3 small outlets for water. So now you've got huge volumes of water trying to escape through 3 small holes. And it's not just water from a single storm, it's water from a culminating event, that being Matthew, plus the water that still had not drained as a result of the heavy rainfall in September. So now I think maybe you can kind of understand why things happen the way they happen with Matthew in terms of the impact that you all experienced. And I want to kind of go back to what I said a couple of slides ago about it not being a single rainfall event. This is a river gauge at Lawrenceville, which is in Brunswick County, about 90 miles, 100 miles west of here. And what you can see is if you look at those bottom yellow lines where I have them measured 2 feet, 3 feet, 4 feet, what you see is you see those peaks gradually get higher, but you also see the bases get higher as well. And what that's telling you is not only, in this case, we started dry, but the first rains, you got a little bit of rise in the water. The rivers responded a little bit, but they didn't go down all the way that they did before the second big rain came. The second big rain came, notice the peak is higher with that second big rain. And then the valley's didn't go down as far as it did the previous time. Now all of a sudden you got the culminating event and the river says, I can't hold the water anymore, I'm going up. And we see that quite often with big flood events. It's not that one event, it's multiple events. Here's at Franklin, you see the same sort of thing. You see down here at the bottom, river was very low going into September. Then it went up with the first event, but notice it didn't come down all the way, and then it came back up again. And not only went up higher, but it stayed up higher longer than it did with the first event. And notice you don't have 3 peaks here, or 4 peaks like you did at Lawrenceville. That tells you that the rainfall in some cases fell in different places more heavily than it did in others during the month of September. So, tidal flooding versus river flooding with Matthew. The top left graph is the tide gauge at Fort Monroe. You'll notice that that had a very steep peak, went into almost at least moderate flooding, and then came down pretty quickly. And you can see the tides stayed fairly close to where they ought to be a couple of days afterwards. Well, in Suffolk, where they had some dam issues on Lake Mead, where they had to end up releasing significant amounts of water, the water went way up above where it should have been, actually went into severe flood. They had significant issues downtown. But eventually, after that water left, because it was going into the Chesapeake Bay, the river came down fairly quickly. This rise here on the right side was not due to tides. It was due to rainfall-related issues. So there were differences with Matthew. So this is an interesting slide, and it really gives you a sense of the impact of the water upstream across the Dismal Swamp, Chesapeake, et cetera, and how that impacted what happened once you cross the border into North Carolina. Some of you might remember the town of South Mills essentially being underwater for about a week and a half or 2 weeks. Well, if you look at the gauge here, there was about 6 days or so where the gauge was above what the previous record was. And it flatlined. What's that telling you? That's telling you that you either have too much water coming down and it's keeping the water up, or you've got water that can't escape and you got more coming in, and so the water has to stay up. So that's one of the reasons why we had the impacts we had and why the impacts didn't go away right away. So you see that same gauge in a slightly different perspective. Here's the 6 days above record stage that I showed a little bit earlier, and then finally it started to drop off. All right, let's talk about storm surge. This is the one we all get excited about, and we probably should, because when it comes to hurricanes and tropical storms, we flee the water, hide from the wind. You look at deaths from hurricanes and tropical storms, 80 to 90% of all the deaths with hurricanes and tropical storms are a result of water, whether it's storm surge flooding or rainfall / freshwater related flooding associated with that hurricane and tropical storm. If you're not familiar with what storm surge is, it is the rise in water that is directly due to storm forces. When we talk about a hurricane, there are two sets of forces that align themselves. One is the wind force, the other is pressure changes associated with the hurricane. They're very dynamic in a hurricane. A nor'easter, there's very little pressure component to how high the water gets. It's almost all wind related. And it has to do with wind direction, wind speed, and duration of wind in a nor'easter, whereas with a hurricane, because it's a single moving along entity, it's associated with the storm itself, directly associated with the storm itself. What we do not take into account when we talk about storm surge is waves on top of the water level. And I'll show you a couple of pictures in a second, but if you go back to some of the big events that we've seen in the last 15 years, fortunately that have not occurred here in Virginia, the damage that you saw was due to a combination of water being significantly higher than it should have been because of storm surge and wave action on top of that water. And those waves along the coast could be 10, 15, 20 feet high. And it's not one wave or two waves. It's hours and hours and hours of waves, essentially beating up shoreline properties. There are three factors that influence storm surge. I got size and intensity. You might say, well, that's two. I kind of put them together. Bigger the storm, the stronger the storm, the more water you're going to get moving onshore, the bigger the storm surge. Storm speed is an enigma here in Hampton Roads. You may not be able to tell anything about what the storm surge is going to be just by looking at storm speed. Some places it makes a big difference, and some places it makes no difference. The third one is angle to the coast. This one too can be complicated in the Chesapeake Basin because where you are in the basin determines what is perpendicular and what's not. But for a straight coastline or a relatively straight coastline, like the coastline in North Carolina all the way down into Florida, the more perpendicular the storm is at impact, the bigger the surge for that particular storm. The other thing to remember is where you are relative to a hurricane at landfall can make a huge difference in terms of how bad the storm surge is. If you're on the right side of that storm as you're moving along it, so in this graphic, this area up here, that's the place you do not want to be. You got two forces acting together. The wind force with the counterclockwise motion around the storm combined with the storm itself moving in the same direction. Both are pushing water on shore. So here are two examples. Top examples are from Katrina in 2005. The bottom two examples are from Sandy in 2012. The destruction you see along the coast is not due to inundation. If we're just talking about a little bit of water moving in and rising, those structures will be inundated, but the destruction that you see would not occur. The destruction that you see, and in Katrina we saw it for blocks and blocks inland, was due to the wave action on top of the water. It's two things together that cause this. But it's water, and it's moving water. Always remember, whether we're talking about flood-related deaths from freshwater and flood-related deaths from storm surge, in most instances, we're talking about moving water that's doing the damage and the destruction, and in many cases, the loss of life. So I've already talked about the right forward quadrant. But let's talk, and I apologize, hopefully most of you can see the numbers, but I tried to use a couple of cases, and I want to kind of bring in Know Your Zone. How many people have heard about Know Your Zone? All right, a good chunk of you have heard about Know Your Zone. What Know Your Zone did is it separated the maximum surge for a given category from storm speed and direction of movement differences that can make a huge difference in terms of how much surge you might get on your property and ultimately whether you need to leave or not. So in the top left here, this is the maximum surge for a category 2. The bottom right is a category 2 moving toward the northeast at 20 miles an hour. They don't look the same, do they? I use the same scale on all of these images. So for a storm moving toward the northeast, you don't get much surge because you're not drawing water from any place significant to bring that water on shore. So a northeastward moving storm is not a huge deal when we talk about storm surge. However, if we move that storm to the north, where it's moving from south to north, you start to get more surge on the coast. And as Councilwoman Henley talked about, as you've seen the last couple of days here in Back Bay and the adjacent parts of the Northwest River. So now you see the dynamics for why water gets where it gets. And the last couple of days, it's simply because south winds have been blowing and pushing the water up from Currituck Sound up into Back Bay. Well, with a hurricane that is moving from south to north, especially one that's west of here, you're going to do the same thing. You're going to draw the water up from Currituck Sound, from Albemarle Sound, and where's it going to end up? It's going to end up in the southern part of Virginia Beach. Third one. I never want to see this. You all never want to see this. This is a Category 2 moving toward the west-northwest, almost perpendicular to the coast. Notice the storm surge numbers along the coast are not that much different than they are for the maximum for a Category 2. For most of Hampton Roads, the worst case storm movement direction is toward the northwest or toward the west-northwest. The good news is that you can go back 150 years and only find one storm that affected Hampton Roads that had that trajectory, and that was the 1933 Chesapeake-Potomac hurricane, which some of you are probably familiar with. So my point is, it's plausible, but not likely. It's a very rare occurrence to have a storm make a west-northwest or northwest hook into anywhere along the mid-Atlantic region, not just Virginia. Winds. So winds, I don't want to spend a whole lot of time on because they can vary significantly from storm to storm. The pattern can be a lot different, and I'll give you a sense in showing you the winds from Irene versus the winds in Matthew, where there were other meteorological forces that were at play. In all cases, though, the closer you are to the water, the stronger the winds are going to be. Doesn't matter. If you're on or near the water, the winds are going to be stronger simply because of less friction. The further you are away from the water, the weaker the winds are going to be, but they could still be strong. So what ends up happening is, if you want to kind of think about this, how Mother Nature makes up for the winds on land being weaker in a sustained perspective is that you get these periodic gusts that are close to what they would be on the land. That happens. That happened in Isabel a lot, where you got these huge gusts that were comparable to what the winds were along the coast. The wind pattern can be very different for a true hurricane versus a system like Matthew, where you had other forces at work and Matthew was transitioning to becoming a non-tropical event. The third bullet is really important. You all might have thought that by going through Matthew, by going through Isabel in 2003, that you lived through a hurricane. The reality is, it's been decades, multiple decades, since Hampton Roads has experienced true hurricane force winds. And you could make an argument as to when it was. You could talk about Donna in 1960. You certainly could talk about Hazel in 1954. You could even go back to the 1933 hurricane if you wanted to. But it's the upstart is that it has been decades since Hampton Roads has experienced true hurricane force winds. So let's show you a couple of examples. This one is kind of a computer-generated depiction of the winds with Irene in 2011. But you can get a sense that the closer you were to the water, here are the Outer Banks here, the closer you were to the water, the closer you were to the center, the stronger the winds were. And you didn't have to go very far inland to not have a whole lot of wind. A lot of that's due to friction, but it can also be due to the wind structure of that particular storm. Let's talk about Matthew. Matthew was interesting because if you look at the winds that were truly Matthew only, they were in this region here, essentially from the northern border of the Albemarle Sound southward. But lo and behold, you had some 50, 60, 70 mile an hour winds up here in Southside Hampton Roads and Virginia Beach in particular that were not directly associated with Matthew. They were associated with thunderstorms that developed the afternoon that Matthew approached that produced really strong winds as they came southward. And those were the winds that did most of the damage. And again, they weren't directly with Matthew. They were with thunderstorms that developed north of Matthew, associated with a cold front and ripped southward during the evening and overnight hours. So your wind profile can be different from storm to storm, and there can be intervening factors in the magnitude of the winds that determine what the wind profile looks like. But even in the areas where it was Matthew only, you can see that the further inland you got, the weaker the winds were. And that's universally true. And that's all, by and large, due to friction. All right, that's my part of the presentation, and I'll be happy to entertain any questions that you all might have.
I just ask that if you have questions, if you would use the microphone there in the center so everybody can hear your question.
First of all, thank you for a great presentation. My question is this: with the 3 rain events, September through Matthew, what rain event would you classify that as? I've often heard it was a 1,000-year storm event.
Yeah, great question. If you look at, and you all can do this, there's a website out there that actually provides rainfall periodicity is the what technical term I would use, but essentially it gives you a graph that goes from 1 minute out to 1,000 years, out to from 1 to 60 days, you know, duration of rainfall. How likely are you to experience it? And to get somewhere between 30 and 35 inches of rain in a 45 to 60 day period is about a 1 in 1,000 or so type event. It was a big deal.
Any other questions? Okay.
And if any of you are interested in going and looking at that, I'm going to make a little plug. There's a handout that I put. The second website that has a wake field on it, there's a briefing page, there's a rain and snow forecast page, and from that page you can get to that link I was talking about. Yes, ma'am.
I was recently listening to a program, and they said one of the big problems with the way the air's going is that hurricanes now are slower. So then they come and settle, and it's a longer period of time. Is that your understanding?
That's my understanding. I don't know. I'm not familiar totally with that study in and of itself. I have not read the study, but I did read a little bit about the news reports that came out. So I don't really know how long the period of record they used to determine, you know, how quickly storms are going, or you know, how fast they were moving in general, nor what areas were they referring to. Was it the entire Atlantic basin? Were they talking globally, et cetera? But that's my understanding of the conclusions from that study. Yes, ma'am.
Are we seeing changes, like maybe a different cycle of rain events? It seems like we have more heavy rain events than maybe years ago.
The short answer to your question is maybe. Those that are, and it's the conundrum of climate science, and that is there are certain things we know, there are certain things we don't know. Part of what we don't know is that we're able to measure change much more frequently than we've ever been able to measure change before. So what do we know on a day-to-day basis or a month-to-month basis about things that happened 300, 400, 500 years ago here? There have been studies done, though, that suggest that, at least in the U.S., that the frequency of high-end precipitation events is increasing. That's the suggestion. Whether that ends up holding true over a long period of time remains to be seen. The other thing to remember is it's not just the rainfall, it's what we're doing to change the impact. Every new development that's built, every new shopping center that's built, every new road that's built changes the dynamic of where that water goes and how much water it takes for problems to begin to arise. So it's really a twofold piece there. Yes, sir.
So, Bill, I think the statistics you were referring to come from what you guys call NOAA Atlas 14.
Yes, that's
The
correct.
rainfall frequency records. And as I recall, those were done around the year 2000, looking at about a 50-year period before that. And we've had about 20 years now since that time. And I will tell you, our people have been looking at it, and that the last 20 years don't fit that pattern. And so I might be wondering, when could we expect NOAA to update these tables? Because we have standards and we tell someone we're designing to a 100-year event or a 10-year event. Well, really, it looks like those are more like a 5 and 50-year events.
Yeah, I'm not sure it's quite that dramatic, although it may be, but it's my understanding that the tables that are on the website that I was discussing are updated with some frequency so that they're not static. That used to be the case, I think, but the advent of technology allows us to update those. Now, what the update frequency is, I really don't know.
Yeah, I think ours, the data we're looking at is the early 00s. And so it'd be interesting to hope that NOAA might come back sometime and bring that up to date because
Yeah, I'm sure that's certainly being looked at, and I think it would be fair to say that you've got to continue to look at that. The more data that you got, because those are all statistical pieces of information, so they're not necessarily based on past data. That goes into it, but there's statistical equations that are run to come up with those numbers. And the more data that you have, the better your statistics are going to be. So you would really want to use or to update those with some frequency to incorporate later data. Absolutely. Any other questions?
Yes, sir.
Do I get asked 2 questions tonight? I've lived here my entire life, and I have noticed over a 40-year period that predominantly during the winter months, the winds are, I guess to rephrase that, when I was a young boy in the wintertime, the winds were predominantly from the north, and the tides in the Back Bay area stayed predominantly low, unless it was some major event. However, in the past 40 years, I've seen a dramatic turn that the winds, even through the winter months, are now predominantly from the south, and it keeps the bay water up even higher. And can you explain is that because of global warming, or it's a pattern that the weather is changing on the wind directions?
You and I are contemporaries. So what I will tell you is if you look, and a real good proxy for trying to understand what's going on is if you look at the snowfall versus temperature data. And it shows up better in Richmond than it does in Norfolk. But from, say, the mid-50s through about the early 80s, 80% of the winter seasons had above average snowfall and below normal temperatures. In order to get that, you have to have north winds. If you look earlier and later, you'll notice a much more variable winter snowfall regime, where some years you got a lot and other years you didn't get very much like we've seen since the last 30 years or so. So my guess is that our parents and their parents experienced things similar to what we've experienced. Just because to get that annual variability like that, including 2, 3, 4 years in a row where you get very little snow, to have that happen, you have to have more south winds.
Earlier in your lecture, you mentioned in Portsmouth, I believe you said there was a dam that they had to
That was in Suffolk, Lake
Suffolk,
Mead.
and you said they had to release water from it that ended up doing flooding Suffolk itself.
That's
correct? Right. So would it be safe to say that since a lot of our infrastructure, when it comes to storm drains in Hampton Roads, they've been based off data that is older than the data that we have now in the new changing storm systems? So would it be accurate to say that it would be more safe for Hampton Roads to start updating the storm infrastructure with the change in storm systems?
I'll go one step further in saying nationwide that's the case.
It's the case nationwide.
It's not just here. It's New York City, it's Philadelphia, it's DC. Most of the infrastructure that exists in terms of stormwater, et cetera, is greater than 50 years old. And there's been a lot of change in 50 years or more, 75 years or even 100 years. So that's something that clearly needs to be updated, not just here in Hampton Roads, but in many parts of the country.
So you said again in your lecture that things such as building roads, new developments such as shopping centers, et cetera, they affect the drainage of the water as well. So would it be fair to say that when Virginia Beach, when we start expanding such projects, we need to maybe possibly step back and really reevaluate the infrastructure that we have in place now before we continue to push forward major developments in the city?
Well, I think, and I can't speak for Virginia Beach, and I'm not an engineer,
Correct.
but if you look around at the development that's occurred, in many cases, you'll see ponds that are designed to take that water and hold it.
Right.
So that's one way to accommodate the change in the hydrologic piece that occurs when you pave over or build over what was forest or farmland, et cetera.
Thank you, Mr. Sammler. I appreciate it.
You're welcome.
So I'm going to go ahead and cut us off and get Mr. McCoy up here. Thank you very much.
Thank you.
So let me bring up his. So Kurt is a hydrologist in the West Virginia, United States Geological Survey Water Science Center. He started his career as a hydrologist with the USGS in Charleston, West Virginia, and then on to offices in Albuquerque, New Mexico. Kurt currently works with the USGS in Richmond, Virginia, where his focus is on the development of regional water budgets, use of geophysical data to monitor and limit groundwater withdrawal, and development of novel approaches for groundwater monitoring. Kurt serves as Secretary of the International Standards Organization Committee on Groundwater, and he recently organized the Hampton Roads Water Symposium to discuss water-related issues in coastal environments of Virginia. Kurt has authored or co-authored over 20 publications and has presented this work at many national and regional conferences. He has a Bachelor of Science degree from the College of Charleston and holds a master's degree in geology from West Virginia. Please welcome Kurt McCoy.
Perfect. Okay, well, first I just want to thank Councilwoman Henley for setting up these kind of information sharing sessions. I think that's really important. It's a good venue for me to share some of the work we're doing, and it's also, is it working? Okay, I see Chuck sneaking up. It's also just a good place for us to kind of communicate openly, if you would. Also want to thank Chuck Payne for inviting me to speak here on some of our recent work. I see a number of familiar faces in the audience. I'm starting to feel like kind of like someone who lives around here, although I live in Richmond. I spend a few days here every 6 weeks and so, and it's getting to be, I feel like an honorary citizen, if you would. There's a little bit of a bend here towards the southern watersheds and a little bit of a bend to a broader science theme in terms of what may be contributing to flooding or changes in hydrology here within the Virginia Beach area. So we'll start with the idea that the USGS isn't new to the area of the Albemarle Sound. Extending way back into the 70s, we've been collecting water quality data in some of these estuarine areas. We also did some groundwater flow modeling in the southern watersheds back in the early 2000s. And so a lot of our data all our data is available online, publicly available, and anything you see here, if you're curious, you want links to, feel free to grab my email address and send me a request, and I can get those things to you. So one of the big things we're working on now, and it's a big part of what people think about in terms of coastal resiliency, and in particular, you guys here in Virginia Beach are right on the forefront. You're right next to these Chesapeake Bay and the Atlantic Ocean. But the big thing we've been working on recently is land subsidence. Land subsidence is not a new issue in the area. This extends way back into the 40s, where the National Geological Survey routinely measured or surveyed in spots across the coastal plain of Virginia. And at one point, they started scratching their heads, and they started seeing these two bullet holes show up pretty frequently in terms of subsidence. So this is land sinking, if you will. And so they came to us. They say us. I wasn't even born at this time, but they came to us, my people, and they said, does this make any sense to you guys? Is there any data you guys have that can help support our understanding of what's going on, why we're having subsidence targeted in two areas of Virginia? And what happens is that those are the two large paper mills, one at West Point and one down here at Suffolk or Franklin, I'm sorry, that are withdrawing lots of water from the Potomac aquifer. And the result is, as you withdraw water from that aquifer, the aquifer tends to shrink and the land surface shrinks with it. So the interesting part of that is that these areas are distal to Virginia Beach, but the decisions made there actually affect you guys out here. If you look at some of the 2 millimeters a year, you think that's really tiny, but if you extend that over an 80-year time period, that's a substantial amount of potential loss of elevation related to groundwater pumping. So in terms of extent, if you want to, I want to go back real quick because this figure is commonly shown and it stops right here at the Virginia-North Carolina state line with the assumption that nothing happens beyond the state line. But truth be told, in 1974, there's an old publication in which they extended these subsidence contours, and they showed them actually to extend well south into the Albemarle Sound. And I think that's an important concept to think about these either aquifers or estuaries. All these are shared resources, and that we really need to kind of attack them as sort of a broad context, multi-state, multi-agency type issues. So one of my contemporary colleagues now, Jason Pope, when he was a graduate student at Virginia Tech, took advantage of some of the extensometer data that was collected there at Franklin and Suffolk. And extensometers are basically really fancy, expensive instruments. There's a hole in the ground that goes all the way through the coastal plain to the rock underneath. And so it's got two fixed points, that rock underneath and the land surface. And it's basically just measuring that package of aquifer squeeze. And it doesn't always squeeze. Sometimes it comes up. So what he did was took advantage of 15 years of data at those two sites to come up with an estimate of the rate of subsidence at Franklin and Suffolk. And what you find is, well, it's complicated. There's a lot of physics involved. It's some heavy math, modeling, computer simulation with understanding of physical properties that even I don't really understand, to tell you the truth. But I can understand a graph that shows me that things tended to decrease at two different rates. And what was interesting is most of the pumping there at Franklin had a rate of 1.6 millimeters per year of average subsidence, and some distance away there at Suffolk, it was much higher, 3.7. So it tells you something about the fact that, I'm going to start this theme now, that we can't just finger point one thing. As scientists, we look at multiple data sets, and we're trying to understand our natural world through multiple lenses. And the more we can pile in there to help us understand what's going on, the better we can kind of clarify some of these pictures. This seems like forever ago now. In 2016, when HRSD decided that part of their new initiative was going to be to inject wastewater into the Potomac aquifer for a number of beneficial reasons, but one big reason was maybe to help with the subsidence issue. Basically alleviate that pressure pulse that's propagating in this direction and maybe abate subsidence. So basically not completely abate it, but maybe slow it down. Those sort of things, because if you think about lands going down and seas coming up, there's a critical point there we're going to see flooding. And so any sort of beneficial use of wastewater in this fashion is obviously a good thing. So we worked with HRSD through the fall, and that was a long fall. Tell me. And really, this was a brand new USGS rig. Really impressive. I'm not an engineer. I'm a geologist. I don't see big equipment that often. This was really impressive piece of equipment. And so they drilled a total number of 8 holes and some close to 7,000 feet of hole into the ground there at the Nansemond site where the first SWIFT experimental station is going on. And part of that, we drilled an extensometer, new extensometer here on the coastal plain. And one reason really is to really capture the impact of SWIFT on subsidence, but also extend our understanding of subsidence due to aquifer injection or withdrawals out in the direction of the areas where, you know, really flooding and land subsidence are going to become a big issue. So following on this, the NASA guys, you know, they always have to show us up. They don't have a space shuttle anymore, but they have a few thousand satellites floating around, and some really smart people too. So NASA comes and they say, you know, we've got this satellite and we can process what they call INSAR data. And INSAR data is basically just shooting a light at the land surface, and they're measuring relative elevation changes across the area. And one of the really neat aspects I find from the 2017 pub that NASA put out, and this is two sides of this coin here. One is, you know, the relative motion, both positive and negative, which is interesting in itself that you see both positive and negative motion, is that it's really what I would call heterogeneous. It varies everywhere you go. And so that point kind of speaks to me, especially if I look at this pub and read it in some detail, is that we've done a lot on the landscape. And one of the reasons why we might see really large amounts of heterogeneity in the subsidence record is that a lot of what INSAR might be measuring is fill material, natural compaction, settling of fill material, on top of the fact that as tides come in, this is things we're learning from the extensometer now, as tides come in, they're creating little mini bulges in the land surface ahead of them. There's a lot of things going on at the land surface that we're able to capture now with technology, both from the satellite base and land base, that give us some insight that this thing is moving all over the place. And it's a complicated issue. And so to support NASA's work, we're working with HRPDC to come in and say, all right, if you can measure it from satellite, you know, at least us lowly USGS guys can measure it on the ground. And so what we set up is a network of base stations, basically. So we're going to occupy these stations with some GPS satellite data, or survey grade GPS stations that are survey grade. I think I got that right. And we basically occupy them over a 4-hour, 6-hour, or 8-hour period. We recently got into this 24-hour period, thinking that we can capture that range of fluctuation in the land surface over the 24-hour period that would really help constrain the INSAR data. Now I'll go ahead and caveat this. You guys live here. You guys don't feel the land going up and down. So we're talking about really, really subtle changes, but over time, it's trying to constrain data sets are going to give us that long-term trend. And so it looks something like this. These are benchmarks that are put in, and they extend somewhere between usually 30 to 60 feet down into the ground. And of course, all you see at the surface is a tablet that we didn't survey in. So we survey those land surface motion at those fixed points. We're going to do this over a 5-year period, so every year. So we're going to try to create that time series of data that we can use to support the INSAR, the NASA work. Opus is a online software that the National Geodetic Survey supports to process the data to give us those solutions. And really, you see that millimeter accuracy. So it's really fine resolution data. And then, of course, we're working with several folks to make this happen. And that's really the key in a lot of our work is that if you step into an issue, you got to bring in the brains from all kind of aspects to make sure that you're covering all your bases, and really the end product is the benefit of all. And so the collaboration with INSAR and ODU and the NASA folks. Also, kind of just going to touch base briefly on another side topic, and I'm glad we talked about it briefly. I'll bring it up in terms of the flooding picture. The TMDL issue with Chesapeake Bay is something we're heavily involved in, so we have a number of storm water quality sampling stations set up in the area, and basically the idea is really what's the contribution to the bay, and can we, having observed it, and then turn around and model it so that we can create some surrogates and extend our understanding to areas beyond where we are actually observing the data. There's 12 stations currently. I'm going to turn around here because the screens are a little blurry or my eyes are getting older. There's currently 12 stations in the Hampton Roads area. Some of them are in the southern watersheds. I'm actually visiting this one. This one was really neat. During the Hampton Roads Symposium a few years ago, that was actually during this 2016 period where we're talking about the Matthew rainfall. We happened to go. We had the symposium in the midst of some pretty awful flooding. The parking lot was flooded and everything. And I said, I've never been to your site, to one of my colleagues. I said, take me to one of your sites. So we went there, and it was just interesting to watch sediment dynamics happen in real time. I'm a groundwater hydrologist. I don't see anything happen in real time. So to watch sediment dynamics happen in real time was really impressive, and it made me kind of clue into some of those data sets that they're looking at, what they actually mean. And so anyway, there's intensive monitoring at all these sites, and then they come back and they collect samples, actually collect the samples with some frequency to basically constrain the continuous monitoring, or extend the continuous monitoring extends the routine sampling over time. So, and then lastly, in terms of things I don't know that much about, because again, I'm a groundwater hydrologist, following on Hurricane Sandy, really Hurricane Sandy was a rude awakening for the East Coast and the U.S. and federal government in particular about the lack of data to support emergency management. So following Hurricane Sandy, there was a lot of federal dollars that were pushed down to support development of networks, tide gauges in particular, that would lend to emergency management decision at the time of the event. So this was a coordinated effort between us and NOAA. We set these things up. We've got, at the time, we were called them rapid deployment gauges. So we kind of just put brackets in places, and we knew a storm was coming. We'd go and we'd put some quick equipment in so that we can monitor a number of parameters. Those things have shifted post-Sandy. Things shifted after sort of the federal dollars began to wither. People realized the value of this data, and a lot of the local municipalities stepped up and said, hey, we really value that. How do we get that to continue? And so we've since replaced those temporary gauges with permanent gauges, and a lot of them record the tide level, wind direction, a lot of the meteorological type data, precipitation. Down in the southern watersheds, there's two. There's the one at Beggar's Bridge here, and then on Pungo Ferry, and they look like this. So if you ever see these things, please don't touch them. Strangely enough, that it looks fairly simple, but this is really complex telemetry. So this data is coming in real time every 6 minutes, and with really complex telemetry is really expensive data. So we try to at times be inconspicuous or basically put the federal label stamp on there, hopefully, but there's always issues of people their curiosity getting the best of them. But anyway, this is what it looks like. When you go online, you click these links, it looks like a squiggly line. There's a lot involved there. There's a whole lot involved in this type of gauging. And so all this data, again, publicly available online. You can get it through us, through our INWIS server, or you can get it through NOAA, because NOAA translates it into predictive tide alerts. And I think you saw some of those plots earlier from Bill's talk. So now we're going to get to the good stuff, as I would say. This is groundwater hydrology. And again, I'll I'll promote this idea that it's this collaborative environment that develops once you have these data sets. And what you have here in Virginia Beach, which is relatively unique to the Hampton Roads area, is you've got a long history of support for data collection. And what that translates into is people like me being involved and looking at data and talking to other people and trying to collaborate. And then you see people who I don't even know give me a call and say, hey, I see this data you got. Can you send it to me? And they're doing all kinds of things down here because of scientists across the nation are looking for data sets to address coastal issues. And Virginia Beach is sitting here with groundwater data, tide data, precip data, all this kind of data for them to explore. And ultimately the benefit is Virginia Beach because our knowledge is continually increasing. So the latest one, if you will, was David Sample at Virginia Tech reached out to me. He said, I want to use your data to model the shallow groundwater across Virginia Beach. I don't really care that much about it, but it's part of this TMDO issue, blah, blah, blah. And I was like, wait. I like the first part of what you said, but the second part lost me. So my route was actually through his grad student, and I just kept working with her. She was a real curious girl, and kept working with her, feeding her data, telling her about the ugly ducklings in the pond, that kind of thing. And what she developed was a really nice, simple kind of GIS exercise, of shallow groundwater that supported their TMDL work. And so she just recently got that published earlier this year. The other thing that I want to focus on is the fact that in 2013 through 2017, we did a lot of focusing on the shallow groundwater issue because we're kind of aware of the Chesapeake Bay TMDLs and is there any issue with nutrients in the shallow groundwater. And that kind of folds right nicely into the fact that shallow groundwater ultimately becomes part of the flooding story as well. So we've got a lot of data. And you'll be happy to know that although we blanketed these aquifers with samples, that basically there's only 2 sites that we showed any incidents of anything that looked remotely like it would be a elevated nutrient issue, and those were already known, so we proved the obvious, if you will. But the other interesting part of that is that it wasn't those 2 sites, they weren't specific to any kind of land use or something. One was an urban site, one was a rural site. So, it's not much sense you can make out of 2 data points, but you certainly can't sort of draw any global conclusions about land use. So, a big portion of my job is to make sure that this big network in Virginia Beach of groundwater monitoring wells is up, it's active, it's functional. Big push that I've done since I've taken over this position about 10 years ago was to update a lot of that telemetry stuff. So a lot of the wells prior to 10 years ago were what we would call kind of routine. We would go out and we would have a transducer in the well. It's recording the water level. We would go and physically pull that transducer out of the well, pull that water level off, go back to the office and put it on the computer so you guys can see it. Since then, I've updated a lot of these wells with real-time telemetry. So the water level at any of these, a number of these sites was measured 15 minutes ago, and you guys could pull out your phone, and we could have a competition now to see who could give me a water level at a given site. But chances are I would win, so there's no prize there. But that's not all we do. Really, this network was built years and years ago to kind of support preservation of the aquifer. What we wanted to do was to avoid any adverse effects due to salinization of the aquifer. So we don't know if it's going to get more saline if we don't measure a number of things related to water quality. So we do that a number of ways via sampling, via geophysics, and generally continuous conductance monitoring in these wells. So there's a number of ways we do it. Again, all this data is available online. Now it's a network of about 60 wells. So there's a lot of data online that can be used to support a number of types of exercises. Now, kind of more to the point, and I really like this map that was generated. This is a City of Virginia Beach map. of precipitation from Hurricane Matthew. And the thing that strikes me that is this U shape. And so as a geologist, I'll tell you that U shape, in a simple sense, that's your topographic highs. So the highest rainfall kind of fell in the highest topographic areas. Now, as a hydrologist, I think water runs downhill. And so, I would tend to think that most of the flooding would happen in these areas as that water tried to get away from those topographic highs. The interesting thing is that that didn't really happen, and I start scratching my head. Why did that not really happen the way I predicted? Well, the short answer is, as a hypothesis, you want it to be wrong, so you can keep asking more hypotheses. That wasn't really my intention. But anyway, as I dug into this, and this is one of our precip gauges that was installed as the tide gauge network, you find out, as Bill mentioned earlier, there was a 6-week period here where we had storm in 2016, in the fall of 2016. And so we had 32 inches of rainfall in a 6-week period for an area that averages, somewhere maybe, I think it's 40, 44, is that right, Tom? Somewhere in that. And so we had a significant amount of our annual rainfall right in a 6 weeks period. And obviously that's going to cause a big problem. I was like, well, is this common? How common is this? And the data to support those type of questions was fairly limited. And what I ended up doing was tracking newspaper articles. And so this is basically the newspaper reporting of flooding events over a 6-year period. And we find that there's a peak in fall. All right, we know hurricane season is late summer, early fall, that kind of thing. But really, these weren't all hurricanes. These were those storm events you guys were talking about earlier. They were some hurricanes. And the fact that we I conceptualize this as we have a flooding season, if you will. And we can actually pinpoint it in terms of a number of months of the year. And what it looks like is something like this. And so when I scan through the pictures of flooding online, the things that occur to me is that, all right, we have flooding. This is an issue, roads closure, public health, safety hazards, things like that. But the water is still enough that parents would allow their children to paddle around. It happens in rural areas. And I really had to search to find a picture where I found actually running water in one of these flooding things. And so here's what started to make me think is, why do we have flooding? And let me back up a second. I spent a lot of times in West Virginia, and when we have floods, that means water is moving really fast in one direction. And I contrast that with here that says water is at the surface and it's not really moving anywhere. And to me, as a groundwater hydrologist, there's two things that start to pop to mind. Is one, well, either there's a dam of some sort. There's the stormwater issue. We've got pond behind a stormwater drainage issue. Or we've got such saturated ground that what you're looking at is the water table. Again, some more pictures, and I think it's really, it's both. And so this is a Kempsville area. There's some really, if you guys want to go home and Google, there's some really great drone videos that some of your residents were popping up on YouTube following Hurricane Matthew. It's really insightful to kind of watch these things. But this is over kind of the Kempsville area. Again, you see your big storm pond here. Obviously, it was unable to accept all this water. It was a huge amount of water. And so it pounded up back here. But, look, this is bare ground. Why is that water not infiltrating? Well, there's vadose zone hydrology issues going on there, but there's also the potential that what we're looking at is we've completely saturated everything up from the water table up to land surface. We don't know. We don't have the data here. But the things that these kind of pictures kind of tell me, we had winds, we had a hurricane. That tree didn't snap off. It fell over at the root ball, right? So that means this ground was completely saturated, such that the tree roots weren't unable to hold it up. So anyway, the flooding issue, the point is the flooding issue is complicated. It's not just how much falls, but it's the ability to accept it in a number of reservoirs, the stormwater reservoir, the groundwater reservoir, those type of things. So I was interacting with Steve Poe at the Public Utilities afterwards, and I said, do you guys have any idea where all the flooding occurred? There's some great images online, but where did it all occur? And he sent me a map, or he sent me some data about the calls from where the calls occurred. And then I later found basically people calling with down trees or flooding issues to the city. Then I later found this map, and so that, again, remember that precipitation kind of fell in this horseshoe pattern here? High ground, high ground, high ground, and it's surprised, well, this is not high ground. High ground's over here. It's just surprised me that you see a lot of the flooding happen and kind of, or a lot of the calls on a separate map that's not shown here, happened in those elevated areas. So that flooding happened high, it happened low, so it's stormwater, it's low gradient. That water's not going to get away very fast. So getting to clicking those links and looking at that data, this is a well down in off Princess Anne in the southern watersheds area. And so what you're looking at is over time through September and October, feet below land surface. So if I'm standing at land surface and I'm measuring down the well, how far is it to water below my feet? And so we went into September and it was 5 feet below, and then Hermine hit and water levels came up half a foot. Then Julia hit and they came up to 2 feet below land surface, and then Hurricane Matthew hit and they keep coming up, coming up, coming up. And I would probably posit the idea that at some point, somewhere around this well, that 1 feet, 1.5 feet probably intersected land surface somewhere, that water table. And this is just our record of it. The other thing that, and Bill showed some really nice hydrographs, same point, where he had the peak came up and then it never actually fully fell down. And what you're seeing is here's that source of water that won't allow that peak to fall down. Here's that next source of water that won't allow that peak to fall down. Here's that. So that's that what we call base flow, that groundwater contribution to those streams. So there's the double whammy effect that groundwater can cause flooding to be pervasive over time. You guys saw some of that up at First Landing. The flooding at First Landing was a couple days after everything else, as the water from those dunes eventually just moved off into the roadways. So anyway, this is classical hydrology. Here's the groundwater reservoir. It's that storage, but it's got to go somewhere at some point. I really love this graph so Laura Moss, who works for Dewberry, who is very heavily involved in one of the sea level rise study for the city. When she was at Duke as a graduate student, she again was using our data to do some modeling of groundwater inundation due to various sea level rise scenarios in the northern part of the city. And this is one of her graphs. And so what you're looking at is various sea level rise scenarios. So this is like, I'm sorry, it's feet. I've actually converted it. So various scenarios in terms of feet of sea level rise, and the percent area that's inundated by either incursion of that seawater and or groundwater rising. And you see at the first kind of level of sea level rise, half a foot or so, that most of the flooding is just the groundwater table rising. And it's really those big, thinking about those distal events where you got seawater rising and flooding a lot of areas along the coast, that you start to get more and more portion of the surface water being part of the flooding issue. But again, to me, as a groundwater hydrologist, this is a champion for this. I share this plot a lot because I think it champions the point that flooding is not just something that we see coming towards us, but it's an aerial distributed. There's an aerial distribution to it based on the water table rising underneath our feet. So one of the ways that I've sort of tried to angle our monitoring to address this is taking advantage of our data. Let's see if I can do this. Yeah. So our data and other people's data co-concurrently are located. So this is Beach Gardens Park. This is Holly Road. So the beach is just this way. You've got, if you look at historic photos, this channel kind of went off this direction. Right now we've got a culvert here where this water's moving in this direction. This is an old wastewater treatment plant, so we've got a lot of kind of relic-looking infrastructure around there. We've got a series of wells here. This is kind of a high elevated area. Across the street, HRSD has a number of shallow wells, or has a shallow well. And then to the north, there's a tide gauge that was recently installed. And so the reason I kind of instrumented this site is because we can have what we typically think of as flooding due to runoff coming off the landscape. But in this particular case, we can also have that storm surge at the same time. And then we got this groundwater input. So it's like this trifecta of flooding related contributors that I think makes a unique situation for us to monitor. And so some of the early data back in 2016 looks like this. And so yeah, this is my life. I look at squiggly lines and try to make sense of it. And so let me try to step back and help you guys make sense of it. So again, through time, this is July of 2016 through October of 2016. These black bars on the bottom, we won't really worry so much about numbers, if you will, but these black bars on the bottom are rainfall. So when they go up, that's more rainfall. And these periods right here would be no rainfall. This blue line is your tide going up and down, going up and down. The orange line and the red line are the two shallow wells on either side of that beach garden inlet. And the thing that rings to me is we had, again, 3 storms, right? Hermine, Julia, and Matthew. So Hermine comes in and she says, you know what, that we've got a storm surge, and our groundwater levels went up. Not much rainfall, storm surge. Julia comes in and she says, well, I'm going to do you one more. I'm going to give you a bunch of rain, but I'm not going to fool with the storm surge. And the groundwater levels go up. And then Matthew says, you know what, I'm going to do you both one better, and I'm going to give you both. A lot of rain and a storm surge, and the groundwater levels shoot up. So the point being is that each flooding event has its unique character. There's the fact that the water levels are extending close to the land surface is a function of its inability to get out, but also the varying rate of how much is coming in. So to move to the southern watersheds, I want to kind of move this discussion into maybe how we understand some of this monitoring in terms of land use decisions. And I really like the fact that we've been monitoring these wells for a very long time. We call them the William Oliver wells because they extend back to the time back in the early 80s when all these wells were drilled. And I'd imagine there was a gentleman named William Oliver who farmed in this area, and he allowed some wells to be drilled. And they've been preserved. And the developer there has been wonderful through development about letting us preserve our data collection and continue our data collection there as well. So the interesting thing, you can use Google Earth, the time lapse in Google Earth to look at this type of data. And what you see in 2007 is prior to any of the significant build out in the area, you had some borrow pits operational. And then by 2014, the borrow pits were not abandoned, but shut down, and the lakes were filled with water, and then we started getting housing development around there. So I'm gonna give you a forecast here, but any type of land use change decision, it reflects in hydrology. It's like the greatest tracer of land use changes. And what you see is when the borrow pit was operational, we had all these wells were declining. All right, so water levels were declining. There's a lot of other noise going in there, but the water levels were declining. So why would the water levels be declining while the borrow pit was operational? Because the borrow pit wanted to get the sand, which means they had to pump the water out, which means the water table went like this. Right? Water levels went down. So they stopped the borrow pit operation and the water levels start going back up. And so that is simply a story of, removing a sink in the water table. Pretty neat, but you can see it's a pretty dramatic effect, several feet in terms of your water level elevation in your aquifer. Since then, we've had significant amount of build out in the Asheville Park area, and we all know what happened there in Hurricane Matthew. It's some pretty dramatic flooding in that area. The other thing is we've had some pretty significant infrastructure going on in that area. And so this is a map of the stormwater drainage in that area. And so here is your transition zone, your green line, your transition zone. So the interesting thing is we have two wells kind of up here in the developed area, one well in the not so developed area. It's a good kind of comparison data set, if you will. And what it looks like is something like this. And so the bar over time, all right, these are water levels. We have water levels during the borrow pit period kind of dropping, and then since the borrow pit ceased activity, the ponds filled in, we have the water levels going up and kind of reaching a new static equilibrium. The thing that I brought this up in our meeting last year, Peter, remember this, and if you've come to any conclusions, I'm still scratching my head. All right, so here's this green and red line is data from this well here, the rural, undeveloped. This blue and purple line is up here right in the middle of the development. And you see how well these two kind of track during borrow pit operation time, and then during build out they started to diverge during the kind of low water table times. The interesting thing is these are reporting water levels from about 140 feet down. So we sat around and scratched our head thinking about how would development at the land surface without much water use affect water levels differently at 140 feet down. So again, there's some change going on here. We can't explain it, but apparently the water table seasonally is lower around the development area than it is in rural areas. So again, it's something, it's a head scratcher. So recently, what we did was we had a call from our headquarters that said, hey, DOI, Department of Interior, and the USGS, taking the lead, want to promote the use of drones, or what they call UAS, unmanned aircraft system, for hydrogeologic science. So that's groundwater science. A lot of people are using them for surface water. Can you come up with a good idea to use them from groundwater? And you're like, well, what can you image of groundwater from the air? And there's a number of things if you're creative. And so I like to be creative. And so I reached out to folks at Back Bay and National Wildlife Refuge, and I said, look, we've got this potential to partner, two DOI agencies to partner in an area where we've got a lot of investment going on. Can we come up with an idea? And the idea we came up with was based on the fact that the area is experiencing recurrent flooding, and that one of the signals of recurrent flooding could be that vegetation is being stressed. So you think about these wetlands, if they're continually being inundated, they're going to show stress way before maybe any other signals of that flooding ever actually happens. And so what we did was we partnered with them. Their office is right here, and we partnered with them to fly drones across a big part of this reach here. This is Asheville Bridge Creek. Feeds out to the northern end of Back Bay. And what you're looking for is we shot a lot of what we call ortho imagery, which is really high resolution photography. So from 400 feet up in the air, our version of the NASA satellite can see can image 4 square inches on the ground. It's really, really interesting data. It also shoots multispectral stuff, so the different light signals that the vegetation will give off if it's stressed, and that's this picture here. This is from a Pacific atoll. They flew over this area, and you're looking at an area of stressed vegetation. I'm not quite sure what their purpose was, but our idea was that, all right, as groundwater tables are rising, as we're more frequently flooding the area, that certain wetland habitats will show this type of signal and give us an idea where that wetland's trying to migrate. And this will give us some concept of, how a wetland responds when it's, this type of wind-driven tide, abutting urban landscape type situation. And so we ended up flying, again, this is another image, Google Earth image, most of this reach here, south of their office. The landowner here mentioned specifically this meander bin. And so again, I'm trying to think about change, right? How can we use this data to think about change? And so if you could see, you see a little bit of an island here. And the landowner said that used to be a big island. Now it's gone. And I tell you, you learn a lot from just listening to people who observe things, because the data don't exist. So you try to listen like earlier, what did they observe? How do we translate that into contemporary science? And so if we zoom in, we flew over this thing, and here's that same meander. And there's a couple things to note. One is, there's lots of phragmites. That's a big issue down there. But we had a wind-driven tide, but you can see how small this thing is now. But the other thing, we paddled the area, and the thing that occurred to me is, you see the brown here, and the brown here. And so this is the midsummer. You're in water. You're saturated. I presume that this is more of the native vegetation as opposed to the phragmites, but it's dying. And those are the things, to me, as a hydrologist, point to something's going on here that that's change. That's change. And so just to prove that he was correct, back in 1937, there's a lot of wonderful historic aerial imagery from here. Back in 1937, that meander bin looked something like this, right? And so, again, we've got decadal historic imagery, even going through Google Earth now. And what I found was the first instance I saw of that meander bin start to fail was in 2003. And you can see this small change. So we could just start fingerprint things, say start 2003, what happened. And that's where I want to go next, is essentially all we're doing now is taking imagery and saying something changed right here. And it's tough to go from that standpoint to explain why. All we know is change. Right? So I get back to the office and I'm like, well, something's changing in Back Bay. What kind of historic data sets we have to think about change, and how can we kind of make sense of that and come up with some idea about how we would synthesize, some of this work. And so, lo and behold, there's a lot of historic data sets online, and I'll walk you through why we need to be careful about thinking about cause effect being a one-to-one thing. It's really anything we see changing on the landscape is a multi-dimensional problem. So back in 1872, there was a hunt club, 10 hunting clubs in Back Bay and Turk Sound that reported waterfowl kills from 1872 to 1962 and the days of hunting. And so I don't have to probably explain this. The conclusions they were drawing here probably are that the more we hunted, the less waterfowl we had. Now, what I'll also add to this is that this is like post-World War II boom, right? It happened all over the East Coast. This wasn't the only place that we were hunting ducks. They were hunting ducks all over the East Coast. So that, this decline is not just over hunting in Back Bay. It's probably some portion of it was over hunting in the entire eastern seaboard. But is that the end of the story? It could have a cause and effect there, and I'll tell you that I don't think that's the end of the story. And here's why. So we moved to the next guy who said, this Settle and Schwab study, so they picked up in 1954 and went through 1990. And again, think about the high part of their ducks here. So this high, these bars are their ducks. This squiggly line is the submerged aquatic vegetation, so habitat, right? And there's clearly a correlation between duck population and habitat. I think, again, going back, this high in duck population would be the low in the previous guy's slide, right? So we're already starting low. And then this guy says, well, all right, well, there's submerged aquatic vegetation issues, habitat issues going on here too. So now we're up to 2 variables, and these are just the ones I found Googling. A few years ago, a colleague of mine, Jack Eggleston, and I put together a paper about thinking about temperature in the groundwater here in Virginia Beach. And so I'm going to pull that out, all right? So I'm going to keep that submerged aquatic vegetation there, and I'm going to pull that out. And so there was 3 temperature records locally that we can pull from. And what you find is, well, the submerged aquatic vegetation went down, and so did air temperature during that time period by a degree or 2. So maybe you can draw a cause effect there. Again, be cautious, right? I'll tell you, I can show you the same plot from any stream in Virginia during this time period will show a step change in flow. I can actually expand that. Any stream in the mid-Atlantic, or really the Atlantic region of the U.S., around the 60s to 70s time period, if I just looked at a hydrograph of flow, you will see something that looks like this. So, we had obviously a stress that was much broader than something that we can control locally, controlling hydrology, probably globally, that had probably some signature in this SAV, but it's probably not completely the explanatory variable here. Now, what about if we start zooming in locally? And so at the state level, what was going on at the state level at this time was we had subsidence at Suffolk, right? So that's that plot I showed you earlier that I just dropped on here. So we could say, all right, since 1980, the problem with SAV is due to the fact that land is subsiding and we're just inundating this area more frequently. Again, I don't know if there's a cause effect whatsoever, but the point being is we can easily draw those conclusions without doing some further testing. Lastly, locally, what Jack was able to find from census data was land use patterns during this time. All right, so the farmed acreage, and again, we can say, well, there were peaks in these duck counts during periods when we had kind of plateaus in the change in land use. So maybe we reached a new equilibrium. We changed our land, things shook up for a while, the habitat didn't like it, but then returned to an equilibrium, we got more ducks. And the point being here is that it's probably not even this simple. We can continue to throw variables on here to help explain what we're observing, and that in the absence of kind of data and some quantitative analysis to look at it, we're really just throwing darts. We need to be, we take a scientific approach, and it's okay to be wrong as we're trying to figure these things out. And so I'll wrap up with this, and we were out there doing some drone flights last week, and Josh Weinstein, local newspaper guy, came out, and I happened to blurt out one of these things that I say from time to time, not necessarily this one, but just random things. And I said, look, we're just taking a snapshot in time now. We're like stepping into this thing at chapter 10. Chapters 1 through 9 have already been written, and it's like the Dead Sea Scrolls. There's only bits and pieces of it. We're trying to figure out what is actually in chapter 1 through 9 to help us figure out what we're observing in chapter 10 and continue to read the book. And basically write the book from here on out. And he actually captured that pretty well. And I thought it was a good way to think about, from a scientific perspective, what we're doing here. We're collecting a lot of data to tell a story about why it is we have recurring flooding, inform land managers about decisions they can make to help, alleviate some of the issues, and at the same time, have fun being a geeky science guy. So. And so I'll leave it at that.
So again, if you have any questions, if you'd use the microphone there in the center, I think you stunned them with science. I want to thank everybody for, do you have a question, sir? Okay.
You mentioned subsistence due to removal of groundwater, and we've all heard about subsistence supposedly in the overall area longer term. Are the two equal in magnitude, or is what you found much faster than the overall subsistence that's occurring in this area?
Well, I think the short story is that groundwater withdrawal is only a part of the overall land motion picture. If we've got to think globally about this. Glaciers are off in Greenland. They were pushing down the earth, creating a bulge here, and as they've moved off, that bulge is going down. That's part of the issue. What we're learning now is that in addition to the pumping, that just moving of the tides causes lands go up and down. There's earth tides, the moon actually pulling on the land surface. All that is part of the story about how this thing's moving up and down. It's pretty unclear. Yes, ma'am.
The southern half of Virginia Beach, those properties below Indian River Road to the Carolina border are served by wells and have on-site septic systems. As a hydrologist, what would be your long-term guess on how they're going to fare over the next 20 or 30 years?
That's a tough one. As a hydrologist, I think, trying to think about it. So I'm going to use the word boundary conditions. So the groundwater is responding to boundary conditions, which is basically controls on how much is coming in and how much can get out. And if how much is coming in is changing and where it's trying to get out is changing, you can guess where I'm going to go with groundwater levels. They're going to change in response. Now, so that to me is part of the flooding issue. From the septic perspective, there's lots of places in the world that deal with on-site waste disposal and areas with shallow groundwater. And so there's alternative treatments and stuff like that. And maybe that becomes more of a common theme, you'll see.
Hi, you've talked a lot about the groundwater rising tonight, and I'm here representing the city of Norfolk. I'm Andrea McClellan. We do work regionally here at Hampton Roads. One of the things that we've been focusing on is the idea and effort called Retain Your Rain. And so what I wanted to ask you and address as the groundwater is rising, and we're talking about retaining the rain in the ground before it hits our stormwater system, how do those two correlate? And can you address ideas on how we can address and mitigate our flooding related to retaining your rain?
Yeah, so I think it's, again, that same illustration I gave earlier, except now we're going to be fooling with, because you're talking about directing stormwater runoff into kind of infiltration galleries. Is that what you're thinking?
Trying to be more sponge-like on all of our parcels of land.
Uh-huh.
So that could be rain gardens, that could be bioswales, that could be rain barrels, anything related to that. But within the ground itself, because that could be problematic if the groundwater is actually rising underneath. It could be sponge-like. It's hard to fill a sponge with water if the sponge is already filled.
Right. I think you took the words out of my mouth. But the idea is you have a buffer there that it's not a black box, that it would require management. right? There's times that it's probably okay to allow infiltration to occur at its max, and there's times when you probably need to divert that water elsewhere. The other side of it is that your stormwater outfalls will mimic those hydrographs that Bill showed earlier. If you create more storage in the groundwater, you're going to raise that base level and that stormwater outfall, which means your stormwater engineering needs to be mindful of those different base levels. Yes, sir.
With climate change and sea level rise and the pressure pushing back on the aquifers and also the lakes and everything, do you have data points from what the mean water level was 10 years ago and what it is now, and also the salinity levels between the Chesapeake Bay and the water tables now, simply because the water treatment plants are going to have to work harder, cost more money?
Yeah, so that's a multifaceted question. One, yes, USGS guy, if he's got data, he's going to say yes. We have lots and lots of data. A lot of it serves other purposes, and it should be used to query things like you're talking about. Specifically, let's talk about groundwater salinity. That's one of our focuses here. We've been monitoring for 30 years now, and there's only one case really that I can see that we've seen changes in salinity, and it's probably due to the land use decision. It's not related to anything sea level rise. The idea that, I'm sorry, you mentioned something about the Chesapeake Bay.
Well, the actual salinity of the Chesapeake Bay and actually the temperature of the bay, as far as salinity levels and the nutrients. You know, we've put a lot of money in keeping the Chesapeake Bay as pure as we possibly can, but with the groundwater runoff and the estuaries dumping into the bay, but now with sea level rising higher, the actual weight of the water pushing back on the drain or the speed of the water. Is there a mean water table that 10 years ago was 2 foot and now it's 4 foot? Is this normal now?
I see what you're saying. Yeah, so I would say, and it's the focus of our network has been on parts of the aquifer at greater depth than what you're talking about. You're talking about really that superficial aquifer. We have data at the very top of the water table, and that's what the Virginia Tech collaboration recently was able to take advantage of. But I would say you could poke a lot of holes in that because of the limited focus of observations real shallow. That most of our data is going to be at greater depths from areas that people would pull from for potable resources or irrigation resources. So it's answer the short question, there's a gap in our data set there. Yeah.
How do you balance development with ground saturation?
So I guess the short answer to that would be any land use change is going to have a hydrologic response, right? I don't think that a lot of people think about making a decision and then that's it. But the natural system is constantly responding to all our decisions. And so it's got to be a constant management thing. It's got to be what happened when we made this decision, and now how do we manage what happened? All right, now what happened after that what happened decision? You know, it's a perpetual thing. It's not you're never done, I guess.
Is there a way to develop and grow our community while being responsible to our environment? Is there a balance there that we should try to live by or improve?
Well, I think that's an economic question, really, because you can't support conservation of environment if you don't have the economy to do so. So it's a catch-22, really.
We got one more here.
If I could just follow up with that statement. I'm curious about how we as a region can be more resilient And I'm trying to think about how we can use this as a take-home message for our city and our growth patterns. And when we think about our southern watershed and pushing into the Pungo region, you showed us ample pictures of groundwater that is creating ponding, where we could potentially be creating developments. And I wonder, as a city, should we be considering if these are reoccurring events that are happening at regular intervals or perhaps more frequently, should we be considering development plans in these rural areas and put population density in areas that will impact how people commute to work or, potentially hurt their home values if they have severe flooding?
Yeah, I guess I can't really comment on that, but I can share some thoughts. I get plenty of calls from residents here about water issues. And because we have this historic imagery, especially when they're talking about flooding, I typically go to it and say, all right, where's that home now? And where was that home in 1937? And a lot of the times what you'll see is an ag field stopped in 1937 where the land was marginal. It was wetland or it was saturated with some frequency probably. There's a reason they didn't farm that land. And then you fast forward to now through that time and you can see an encroachment on those wetlands and eventually maybe even filling of those wetlands. And so it's those continual land use decisions that at this point you go to it and you may say, this is not a wetland. There's no issue here, but you got to look at the historic context and that, maybe there was something there hydrologically that would cause us to think about having some caution or something. But I can just think about using available data to inform those future land decisions, I guess is what I'd leave it at.
Okay, thank you. It is 8 o'clock on the dot. I want to thank everybody for coming out. I did, from my shop, leave some flooding literature anytime I have an opportunity to talk about it, flooding or pass out information. But I think folks will be here for a little bit longer, but I want to thank you all for attending this evening and thank our speakers, Mr. Sammler and Mr. McCoy.